have Pietro to tell us about gravity as a mesoscopic system.
Yeah, thank you. So this presentation is based on a paper that came out 2 weeks ago in collaboration with my PhD advisor, Summer, and with Berkeley. And it's about interpreting some classical observables in gravity in a stochastic way. So, to me, the most natural starting point is the concept of universality in statistical physics. I think that we can all agree that solving metabolic dynamics is hard. But luckily, the physics of some classes of observables in many body systems is luckily independent on the microscopic details of the theory and depends only on a handful of parameters. So I think we all studied the case of critical exponents in phase transitions, but this is not the only example. Another very well-studied example is random matrix theory universality for chaotic systems, which essentially says that a quantum chaotic system is very well described by a random ensemble of, well, a random collection of matrices, which is only specified by the probability distribution, even though in a lot of cases a Gaussian probability distribution is a very good approximation, and by a set of discrete symmetries. And this, for example, can be checked in the statistics of the eigenvalues of the spectrum, and also in the statistics of the eigenvectors of the system, which is connected with the eigenset generalization hypothesis, which I will also mention later. A notion of universality, I think, is also present in general relativity. And to me, the first instance that this idea came up is in the Mohier theorem, which essentially says that no matter what happens inside of a black hole, all stationary black hole solutions of Einstein-Maxwell equation can be described by just three independent parameters, which are the mass, the charge, and the angular momentum of the black hole. Now, I don't know if when this theorem was developed, people realized that it was an instance of universality, but in hindsight, I think it clearly is. And in recent years, people have tried to put together these two concepts, namely universality in gravity and also random universality. The idea being that generically, gravitational theory in a black hole background should be chaotic, and therefore it should be in a phase where random matrix theory universality applies. And this was checked at the level of the spectral correlations and also at the level of the eigenvectors. To my knowledge, mainly in the context of ADS-CFT, because you also have a dual theory where you can check your claims. And, well, there have been a lot of papers where also people in the audience contributed. Today, I want to present a new connection between gravitational universality, between gravity and universality, which is inspired by ETH. And the idea is quite simple. Is that thermal correlation functions in semi-classical gravity and ADS, we can think of them as stochastic processes, where gravity computes the moment of this stochastic process. While we believe that this statement should be quite generic, especially in dimensions, let me make some assumptions. I will consider only gravity in asymptotically ADS3, because it allows, well, in ADS3 we can give analytic results, and we also assume ADS-CFT, so that gravity in ADS3 is dual to a two-dimensional conformal field theory, and we also assume the gravity theory to be quickly coupled, so that the dual CFT has a large central charge and also has a spectral gap between the vacuum and the set of excited states. And these set of excited states are supposed to be, which are thermal states in the CFT, are supposed to be black holes in the bulk. Then, as I said, we focus on the class of observables of thermal correlation functions, so objects of this sort. In the most general sense, we can consider as many operators as we want. We place them around the thermal circle, and we can also consider Lorentzian continuations. But for the purposes of this talk, I will only consider the simplest of these of this correlation function, which is the two-point function, where we place the operators symmetrically around the thermal circle, and we consider our Lorentzian continuation only on one of the two operators. So this correlator here, and I will call this correlator G beta in of. This is to set some notation. Moreover, the action that we consider is the following. So, as you see, the first term is just the standard Einstein-Hilbert action with a negative cosmological constant. And also, it's very handy to consider these operators to be light enough not to heavily backreact on the geometry, so that if we insert them, we don't really create a black hole. But at the same time, heavy enough that their dual description is basically massive particles in ADS, so that their action localizes on the work volume. And this is very handy because if I want to compute a correlation function, then in a saddle point approximation, this becomes basically the exponential of minus the mass times the geodesic distance between the points. Moreover, if we want to compute thermal correlation functions of the kind that I showed before, in the bulk we have to, well, we put a black hole, so we use the BT symmetric, and in particular for the correlation function that I showed before, it's the simplest three-dimensional black hole that you can have, is the neutral and non-rotating BTC black hole, which is written there. And crucially, we put it at finite volume, so that we consider the CFT on a finite length. In this case, we normalized it to have length 2π. This is in Lorentzian signature, but if you look at it in Euclidean, then, as you probably know, the boundary becomes a torus. So this is just to set some notation for some figures later. So if you compute the geodesic in this background, then what you find for the correlators that I told you before is this result here. It's a hyperbolic cosine with a negative power, so that plus some correction, I'm going to tell you later, which after a short transient has an exponential decay. Now the fact that it has an exponential decay, it's kind of natural for these kind of systems because, as I said before, this system is in a chaotic phase, it's thermalizing, so you expect that if you perturb it slightly, this perturbation is going to wash out, and at late times you're not going to recover it. Then also corrections are given by geodesics that wrap around the black hole, in this case that wrap around the torus, and the answer is given here, where that answer of here is just a contribution and equal to 0. Now, this answer here does not, slightly modifies but not much this exponential decay, so later on I will only focus on the result up there. Okay, so this is the result that we get in gravity. And in a very nice paper of Maldacena in 2001, he was the first one to realize that if you take this result literally, this is inconsistent with a microscopic unitary description. The reason is that since we are at finite volume, the spectrum of the theory is discrete, so that you can write the correlation function in the energy eigenbasis in this simple way. And the Riemann-Lebesgue lemma tells you that such function cannot vanish forever. It needs to have some thermal fluctuations. And one was also the first one to argue that these thermal fluctuations should be of the order of e to the minus another one number times s. So what we do in this paper is to propose a framework in order to interpret, how to recover these thermal fluctuations and how gravity knows about these thermal fluctuations. Now, let me maybe mention that there is a paper by Phil Sad of 2020 which also addressed this problem but from a different point of view. And if people are interested, I can also mention what are the connections and what are the differences. But for time constraints, I don't really talk about it. But in case people are interested, please ask me some questions and maybe later we can be precise about that. Okay, so as you can imagine, this framework is the framework of stochastic processes, and I think it's useful to review like the paradigmatic example of a stochastic process, which is Brownian motion. So if you want to study the motion of a macroscopic particle in a fluid, of course solving the microscopic theory is impossible. It's intractable because you have, as you know, you have a system of coupled differential equations, and you cannot even simulate it. So what people normally do is that you consider an effective theory, which, for example, you can resum the effect of the fluid molecules on the particle as a force that opposes its motion, and a good approximation is a linear force with a coefficient gamma, which is normally called the dynamic or viscosity. And this is a very tractable effective theory because it has a simple solution, which is an exponential decay. This is a nice result. It's a result that it's a good approximation at early times, but at late times is again inconsistent with a microscopic interpretation and also with the basic requirements of thermodynamics. The reason is quite simple. It's because at late times the fluid molecules and the macroscopic particle are going to be at the same temperature, and for this reason you know the Maxwell-Boltzmann distribution tells you what is the expectation value for the square of the velocity at late times, and it's supposed to plateau at this value, kdt divided by the mass of the macroscopic particle. So this means that this effective theory is not able to capture thermal fluctuations. So you can ask, how can you recover these thermal fluctuations? And I think it's quite remarkable that the most natural way to proceed is to slightly modify this effective theory, adding a stochastic noise psi of t to the differential equation. Now, you can take, for example, the stochastic noise to have mean zero and to be uncorrected in time, so that the expectation value, the product of the expectation value of sine t and sine s is a delta function, t minus s, weighted by a parental g that sets the size of the thermal fluctuations. And you might think that, conceptually the idea here is that we are assigning the effect of the fluid molecules on the particle in two different terms. The deterministic one, which is just the mean of the force, and also a probabilistic term that arises because of all the particles that are bumping into our macroscopic particle. You might think that this is a small modification of the theory, but actually has a pretty drastic change, because the fact that psi is a probabilistic function also makes the velocity itself to be probabilistic. So that if you want to connect this theory to experiments, the only way is to treat V probabilistically, so that you have to compute moments of this V. And in this way, the first moments is unaffected, so from this stochastic noise, so that the mean of this process is just decaying in time. And from this framework, this is not inconsistent with a microscopic description anymore. The reason is that V is basically a noisy signal, and at late time it just has an equal probability of being positive or negative, so that it just vanishes because of this, not because it really vanishes physically. But at the same time, to recover fluctuations, you can, for example, compute what people call the autocorrelation function, so that it's the expectation value of the velocity at time t and the velocity at time s. And this quantity tells you how the noise correlates between, how the signal correlates between the signal itself at time t and at time s. Now, quite interestingly, for Brownian motion, this autocorrelation function is composed of three pieces. The first one is very simple, it's just a product of the two means, which is also the result you would get if V would be a purely deterministic quantity. But then you also have two additional pieces. They are both exponentials, and quite interestingly, they are the same exponential. One is e to the minus gamma t plus s, and the other one is e to the minus gamma t minus s. And these two pieces arise because of this connected correlation of the noise. Okay, and in this theory, then you can also compute the expectation value of p squared in t, which plateaus to this value g divided by 2 gamma, and you can figure out what is g matching with the Maxwell-Boltzmann expectation, so that you basically recover an instance of a fluctuation dissipation theorem because you are comparing the fluctuations of the noise with the dissipation of the system. Okay. So what are we doing here? What we're doing here is that we are considering a mesoscopic description, which is an intermediate description between a microscopic one and an effective one. The microscopic one is impossible to solve, while the effective one is practical but has a certain amount of information loss. And this mesoscopic description is quite nice because it's practical and at the same time is able to recover some information on these thermal fluctuations. But interestingly, this description lies between, it is probabilistic and lies between two deterministic ones. So you do not expect it to hold generically, but only in some specific cases. In particular, there are three necessary conditions that a system has to respect in order for a mesoscopic description to hold. The first one is that you need to consider a thermodynamic limit. In particular, in the case of Brownian motion, you really want the number of fluid molecules to be large. Then you need to have a clear scale separation between what is your probe and what is the environment. So in the case of Brownian motion, what is your macroscopic particle and the fluid molecules. And you also need to observe the dynamics at a rate which is longer than the intrinsic fluctuation of the system. The reason is very simple, it's just because if you just observe one single interaction between the particle and the fluid molecule, and a fluid molecule, sorry, this is clearly not probabilistic, and it's also, in a lot of cases, it's also solvable. So you really need to observe your system at a rate which is slower than this intrinsic fluctuation. And for the case of Brownian motion, it's the mean free time for a particle. And for the case of quantum systems, it's a very good approximation is that it should be related to the inverse spectral width. In particular, the point is that you have an Heisenberg evolution to the minus I E1 minus E2 t. And if you want this phase to change the fastest, you really want to maximize E1 minus E2. So, this is, well, the description of a mesoscopic, it's the idea of a mesoscopic description. Let's try to apply to holography. Well, if you want to apply to the case that I said before, then you might want to consider this result as the mean. Well, first of all, you might want to consider the correlation function as a stochastic process. And you might consider this result as the expectation value of this stochastic process. And as before, the fact that it is an exponential decay and vanishes at late time is not, as we said before, it's not surprising anymore because it just tells you that these thermal fluctuations can either be positive or negative, and on average they vanish. But then the analogy with Brownian motion tells us that we should also consider the expectation value of the product of the correlation function at two different time points. So g beta in t and g beta in s. Now this observable somehow takes into account two boundaries. So you might ask yourself, what kind of saddle point geometry shall we consider to estimate? Well, a prescription that has been considered recently is just consider any saddle that fills these boundary conditions. Now, as a word of caution, I should mention that for the case of 3D gravity, at least to my knowledge, it's not clear the amount of saddles that exist that could fill these two boundaries. And second, this is specific for the case of 3D gravity, there is not a parameter that you can use to organize saddle points in a perturbative expansion. So we might feel a bit lost. But actually, what we propose in this paper is to consider these three saddles. The reason why we consider these three saddles is first of all because we can study them and have some analytic results for these. But also because we believe that we know the physical origin of these saddles, and we can also explain them microscopically, so that we believe that these saddles capture basically, essentially the physics that we care about. And as you see, one of them is the two tori which are disconnected, and the two others are saddles for which the boundary connects these two boundaries, and in this business are called wormholes. So, if you want to study them, there is a very nice paper by Chandra, Correa, Hartman, and Maloney that gives you the result of these saddles in terms of degree correlators, which I'm also going to mention later. But I want to give you an approximation of late times, so when T and S are both very large. Now this is the result, which looks a bit daunting, but I think to explain it is quite simple. So for the first saddle, for this one we have two disconnected tori, each one filled with its own EPC black hole, so that the corresponding contribution is just the product of the two means, in particular the product of the two results that I gave you before. Then for the middle one, we are considering a saddle where the operator at 0 in one boundary is connected through this massive particle to the operator at t in the other boundary, and vice versa. Now, if you consider T and S to be both very large, then you expect that this geodesic distance should not really change much between the geodesic that connects the operator at t with the operator at 0 here or the operator at 0 there. Of course, here, in the way that I drew it, it does change quite a lot, but if T and S are both very large, it should not. And this is why you have this product of two hyperbolic cosines, one at T and one at S. And this saddle is also weighted by 1/z squared of beta. The reason being that the on-shell action of this saddle is 0. So that with respect to the previous one, it's as an additional factor of 1/z squared of beta, which makes it subdominant. And the third one is kind of similar in the sense that it again has 1/z squared of beta that comes from the fact that the on-shell action is 0, and has an hyperbolic cosine in terms of T minus S. Now the fact that this saddle contributes with an hyperbolic cosine is, I wouldn't know how to explain it in simple terms. It's in another paper by Maldacena and Maltz. But the fact that it depends on T minus S is quite simple to explain. It's because this saddle pairs the operator at T and the operator at S together with each other, and the two operators at 0. So if T and S are both very large, then you expect a shift symmetry between, if you shift T and if you shift S, you expect a symmetry. You expect a shift symmetry to hold for this saddle, so that the contribution depends only on T minus S. And as you see, if you approximate these hyperbolic cosines with exponential functions, then you really find a similar structure where you have the two disconnected contribution plus two exponentials, one in terms of T plus S and the other one in terms of T minus S. Notice also that you can really match the two expressions in the limit where delta goes to 0 and beta goes to 0 in the double scaling limit where gamma equal to pi delta divided by beta is fixed. This to me is a very physical limit because it's the limit where the dimension of the operator is very small, so also the mass of the operator is very small. And also, the black hole is very hot, so that you have a very big scale separation between the two. And you expect that this is the regime where this mesoscopic description should apply. So what we told you before should apply. And also, you have this limit of the hyperbolic cosine in the limit where delta goes to 0, really becomes decaying exponential, so that in this case we can identify various parameters V0 and G divided by 2 gamma with parameters of the gravitational theories. And this tells you that the late time fluctuations of thermal formation and gravity are in the same universality class in Brown equation. Maybe I should mention that originally we were not really looking for this. We only had in mind the theory of stochastic process as a framework to explain the behavior of these observables in gravity. But it was quite interesting to see that if you really put down some equations, you can show that at least with the Gaussian approximation, the late time fluctuations are really Brownian motion.
Sorry, so here the temperature is very large.
Yeah.
So the black hole is very small.
Well, the black hole is very hot, and so it's also. Now I always I always forget what's the. I think it's like the relation between beta and this parameter R plus. I don't remember if it's like 2 pi divided by beta or the opposite. In this case, if it's this, then the black hole should be very large. But if someone remembers it, then we'll better check. Intuitively, I would expect it to be large because it has more mass, but on the spot, it might be wrong.
That's because we're ADS.
Yeah, exactly. Okay. I should also mention also that this Gaussian approximation is supposed to receive corrections because the autocorrelation function should not have a complete set of information on the theory. And okay, well, long story short, is the point is that if you then start to compute higher moments, then these higher moments, in the computation of these higher moments, you will also encounter connected wormholes that connect more boundaries. So you expect to receive non-Gaussian corrections. The reason is that, just to be clear, a Gaussian process should only have two boundary wormholes, and something like this 5 moment should should split into the various 2 boundary contributions, kind of like what happens with big contractions in quantum theory, in the quantum field theories. But the fact that you have also geometries of this kind tells you that you have non-Gaussian corrections. So maybe let me make a summary up to this point. We have seen that a mesoscopic description is an intermediate description that contains information on the microscopic theory in a probabilistic sense. And we have also checked that thermal correlation functions in semi-classical gravity ADS are consistently described by a mesoscopic description, where the trivial topology is able to capture the mean of the process, and wormholes represent higher moments of this process. So this is maybe a good time to stop for questions, if there are. No? Yes?
2 questions. First, I think in some of the references you cite, the claim is not that ADS3 is dual to a single safety, but it's dual to some like average or ensemble that satisfies some bootstrap constraints. So I guess, can we make that clear here? Are you saying that the ADS3 is averaging over a single system or over?
So, okay, there's going to be a slide about it later on, but maybe now it's a good time to make that clear. So, there are these claims that gravity could be dual to an ensemble of theories, and I do not know I do not want to claim that this mesoscopic description applies to any observable in gravity, but for the class of observables of thermal convection functions, I think that an ensemble of theories is a superfluous concept, and you don't really need an ensemble of theories to explain what's going on here. The reason is that, can I have the light? Sorry. So if you consider this GD of E, so defined as this, as it defined before, and you specify what is O, then clearly, first of all, you fix the theory and you fix also what is O. Then clearly this is going to be a single weekly line of late times. And if you want to smooth it out, you might want to consider an average over theories. But at the same time, what you could also consider is, for example, the correlation function on a microstate E, where the energy here is the same thermal energy of beta, so something like this. And the same, well, the same thing. And then you might want to, for example, average over the state, the microstates in the theory. Then in this case, you don't really need, well, an ensemble of theories. You can just fix one theory and then do a probabilistic average over this. Now, this, for the case of Brownian motion, is a very natural concept because it's in the idea of Brownian motion itself. So if you consider a fluid and you prepare it in a thermal state, every time you prepare it in a thermal state, it's not going to be the same thermal state. It's actually, I mean, quantum mechanics would be a linear combination of states in the microconical window. And then you prepare it the best you can. It's not going to be always the same. You observe the motion of this microscopic particle, and then every time it's going to be different, and then you average over this realization. Here, I think the point is the same. If you have a holographic CFT, you prepare it in a thermal state. It's not going to be always the same thermal state. You observe this GE of T, and then you average over them in a probabilistic sense. Now, I do not want to make the claim that any observable in gravity can be interpreted in this way, but at least this class is.
Sorry, clarification where you asked which paper were you referring to? Were they actually advocating for an ensemble
Hartman and friends, the KR-QRC CFDs.
But in that case, do they advocate for an ensemble of theories?
Yeah, I think they're saying that it's like an ensemble of CFDs that satisfies some bootstrap constraints. Should be the dual ABS theorem.
Is that the Chandra Collier Hartman paper?
Maybe I'm misunderstanding.
I mean, I think they don't want to say that at finite C there are many different CFTs, but like in some expansion about large C,
Yeah.
like if you only impose the bootstrap constraints to some precision, then you can average over, like you can average over data.
Yeah, but I thought that averaging over data was interpreted similar to what I was saying as like some coarse graining, and you have the behavior of the OP coefficient, which is very erratic, and what you do, you model that erratic behavior as an ensemble. Isn't that what they're doing, or are they actually considering an ensemble of Hamiltonians?
Yeah, I mean, in that space of like OP coefficients or whatever, there's really only one theory. That's their proposal. So there's not really an ensemble of theories.
Right.
In that sense.
So it is in this sense, right?
Yeah.
That's fair point.
Even though the title of the paper is 3D gravity as an ensemble average.
Yeah.
So
Yeah,
I mean,
maybe it's different in the sense that you're averaging over like parameters of the theory as opposed to pure like averaging over the window or something like that, like integrating over time or something.
Yeah, I guess what I was asking in
Dynamic
that
and
case, the interpretation is really having many different CFTs with some probabilistic distribution, or just having a lot of different erratic data within a microeconomic window for a single CFT. You're arguing with that.
maybe the claim is that if you only have access only to semi-classical gravity, you cannot really discern whether you have an ensemble of theories or just an erratic set of data. There are different, I think there are different levels of this claim. You can claim that a geometric description of gravity is equal to, for example, an ensemble over here is in the sense that there is a coarse graining. So if you see that the list of OB data looks like a random list, and so you might want to average over this random list, and that is what gives you a geometric description. There is also the level where you say, no, really, quantum gravity is dual to an ensemble of fields, and these are much stronger claims. My feeling is that they would only claim the first one.
Yeah, that was also.
Can I ask a possibly related follow-up question? I mean, we started this discussion by discussing just contributions from the single saddle of BTZ, and even now when we're talking about these wormholes, it's still like kind of BTZ on both sides. So like at that level, right? Like, why should I even think that I should like? Why is this even still an information paradox, right? If I'm only considering contributions from a single saddle, maybe if I add all the other ones, then I do get, which is a little bit of what you're saying, but I think like. I feel like we could take the argument a little bit further.
So are you asking, I mean, why should I consider a wormhole from first principles, or?
Not why I should consider a wormhole, but why should the contributions to this two-point function from a single saddle be enough to, yeah. Like when you draw the very first picture of the like BTD solution, and the full 3D gravity theory has lots of other saddles. So you know.
Well, but okay. What kind of saddles are you considering? Are you consider the images, or are you consider like real saddles where you have like, for example, a handle or something like this?
I'm thinking of just like the ADS3 base space, where there's like pure ADS3 and then BTZ and then lots of other black holes with spin and different masses and stuff.
Okay, well, for example, black holes with spin. In a canonical perspective, should not really contribute much, because you know anything that is not really like anything that is not that does not match the canonical expectation value is highly stochastic. This is just a standard thermodynamics. Like it's the equivalence of ensembles. It's the fact that if you consider the canonical ensemble or for example the microcanonical ensemble, basically the two answers of large n should be equivalent to either if you restrict to the microcanonical window or to the canonical in the canonical, or if you consider the canonical ensemble. Something similar could be said also for rotating black holes, for example, in the sense that you expect only saddles with the zero angular momentum to contribute.
And does it not matter that the observable, like the thing you want to measure here is something that's exponentially small, so that even though, I agree with what you're saying, but we're looking for reasons.
Well, yeah, I see your point. Like, so what you're saying is that okay, the contribution of for example, black holes with angular momentum is small, but the thing that we want to check are even small. So, okay, maybe I cannot really come up with like a very sharp answer like right now, but
the other black holes they decay. They get something that decays in time still. So if you look at really light times, everything like that's sort of zero.
Other questions? Okay, so let's see how far I go into giving a microscopic interpretation of this. So the microscopic interpretation that we would like to give relies heavily on the eigenstate thermalization hypothesis. For people maybe who are not familiar with this, the eigenstate thermalization hypothesis was developed to explain thermalization in closed systems. And the idea is the following, is that you expect that the idea is similar to this idea here. So if you start from a linear combination of eigenvectors in a microcanonical window, you expect this state to quickly thermalize and observables computed in this state to quickly thermalize to the thermal expectation value. But if you try to check it in just standard quantum mechanics, you see two problems of this mechanism. First of all, if you start with for this mechanism to occur, you really want to cancel all those phases up there. And this implies that the thermalization process is very slow. It's proportional to, in this framework here, is proportional to e to the s, which for systems which have even a reasonable dimension could even be longer than the age of the universe. And notice that this mechanism that I'm explaining, the late time thermal expectation value still depends on the initial CIs that you choose. So clearly there has to be some additional information on the theory for to describe thermalization. Schrennicki's idea was the following: was to say that the matrix elements in for certain classes of operators, which people call simple operators, are actually diagonal, with the thermal expectation value on the diagonal, plus some corrections which are given by random fluctuations of diagonal, which are weighted, which are these random numbers Rij, and weighted by the minus s divided by 2 times generic function f as a function of the average energy E and the energy difference omega. From this point of view, then, you see that at least, well, it's not really apparent why this distinction should actually be much faster, but later I will show why. And it also, you clearly see, however, that all these OII, which are the diagonal matrix elements, factor out, and you get really the thermal expectation value at late times. So the nice thing about the thermalization hypothesis is that it's intrinsically, and also let me assume that the operators that we consider have zero thermal expectation value, so we only retain the random fluctuating part. The nice thing about this hypothesis is that it's intrinsically probabilistic, so that in this framework, these matrix elements, as I said, are random variables which have zero mean and a variance which is specified by e minus s times a function f2. And this is quite convenient for us because if you write the thermal correlation function in terms of in the energy eigenbasis, then it becomes a series of a bunch of terms times random numbers. And this specifies a stochastic process. The reason is that it's a different definition of a stochastic process than what I gave you before. Before I gave you a definition of a stochastic process as a solution of a stochastic differential equation. Here, the definition is different, and it's just in an expansion in a basis of function times coefficients which are random variables. If you have something like this, then x of t is a stochastic process. And okay, so from this point of view, we can ask ourselves, okay, if we only assume ETH, how far can we go? Well, first of all, we naturally explain that G beta of t is a stochastic process, but also, can we say something about the mean and the variance of this stochastic process? Well, it turns out that we can, and it's quite simple. The mean, I spare you the details, it's not very hard to find, that it's a Fourier transform of this function f2 in omega, so that generically it decays at late times. It decays at late times. And also, we can compute the autocorrelation function. To compute the autocorrelation function, we need an additional piece of information. We need the expectation value of the product of the squares of two matrix elements. And at large n, it factorizes, plus there is a correction that comes if the matrix elements that you are considering are actually the same matrix elements. So if I is equal to k and j is equal to l, or vice versa. In this case, you have the structure of these delta functions, weighted by e to the minus 2s, and another function that I call h4, which can be unspecified at this point. And if you use these ansatz in the correlation function, you can compute the autocorrelation, and the result is this. As you see, it has the same structure as Brownian motion because it has two disconnected contributions. the product of the two disconnected contribution plus two others, and which are two Fourier transforms, one in t plus s and the other one in t minus s. Notice that also they are weighted by 1 over z squared of theta. So
at this point, what was the motivation behind the ansatz?
what do you mean at this point? What is the motivation behind the ansatz?
So I think I understand that in gravity you find something of that sort.
Yes. Well, why would we want to use this ansatz in gravity? Okay, it's maybe.
No, even more generally. I thought you were saying here, like, this is just a more general story, right? Like, using this ansatz in this ETH set.
Well, yes, it's a more general story. Or maybe you can say that it's this story seems to hold for any system respecting ETH.
Yeah.
And you also expect gravity in general to respect ETH because black holes thermalize and so. Or at least gravity in a black hole, in a black hole background to be in a phase where ETH applies. So we are trying to give a microscopic interpretation of.
So is it just the statement that the corrections are like approximately Gaussian?
What do you mean with this?
I'm just asking how you motivate that answer.
Sorry, do you know? Sorry, do you mean like this delta function, delta ik stuff? Or did you know this?
Yeah, that's right. The previous slide.
What is
This answer.
this one here?
Yeah.
This answer is just. I mean, it's just a Lagrange ansatz. Okay. Okay. If you want, you can see it as an input of the theory. So that let's consider the case where the expectation value of the product of the square of two matrix elements factorizes, and then there are corrections given by this delta structure. There are, however, papers that say that this is generically true at large n, and it's some line of work of I think Silvio Pappalardi, Laura Frini, and Georgi Kulchan, where they compare ETH with the result of free probability, and this is exactly the kind of structure that we have in free probability. The reason is that mathematicians study that if you have random variables of this sort, so like OIJs, and it could be correlated with each other. Actually, if you go to large n, so you consider like a large number of random variables, then they actually become Gaussian.
Yeah, I see.
Sorry, but that second term is a non-Gaussian correction, right?
Yeah, but it's small compared to the first one.
Right, so in principle you have also higher order terms and they go...
I'm not sure it's a non-Gaussian correction. It's just the fact that we are distinguishing the case between we are considering two different matrix elements or the same matrix element. Because this correction there just arises because whether you are considering, this, for example, I equal to K and J equal to L, or two different matrix elements.
So but it would be an expectation value of 4, so let's say we take I equals K and J equals L, then it's like expectation value of 4 to the 4th.
Yeah.
Is like E of O squared and O squared plus some other correction, right?
Yes, but remember that this is, each one of these guys, these two corrections actually are the same. So if you want to compute what you're doing, so you want to compute in factors of e to the minus 2s, s of e, so of how many states there are in this macroeconomical window, actually these two corrections are of the same order because also this guy here is e to the minus s and this guy here is e to the minus s. So why does this term here is actually subdominant? It's just because later when you have, when you consider like the product of these two functions and you have a bunch of series, then this structure of delta functions actually lower the number of states you are summing over with. And this is actually the reason why you have a factor of 1 over z squared of beta.
Sorry, I just not understand something. Say that I take K and L to be equal to Ij.
Yeah.
K equals Y, L equals to J, that's over the fourth. The first term gives you the Gaussian piece, right? The second term is not Gaussian, right?
Okay, so if you want, the way that I see it, if you want to compute the Gaussian and uncorrelated, the fourth moment of a Gaussian function, so like the fourth is like 3 times sigma to the fourth. Okay.
Yeah.
So 1 sigma to the fourth comes from here, and then you have this h4. You would probably want to take it to be f2 squared.
Yeah, that's what I'm asking. Like,
And then you have 2 additional contributions that give you this condition.
right, so if it's actually Gaussian, that H4 takes a specific form.
Yes, but I do not want to commit for it to be completely Gaussian. So
Okay.
okay, I'm running a bit late. So okay. Essentially, this is all of the microscopic physics is captured in this mechanism. For the case of holographic CFDs, we can also match what we find in gravity. And okay, so in this last few minutes, I explain how you find it for holographic CFDs. Well, the case of holographic CFDs, so this study applies to holographic CFDs because holographic CFDs respect the 3 necessary conditions that I mentioned before. You have a thermodynamic limit, which is the large C limit. You have a clear spectral gap between the vacuum and the few matter operators that you use for these thermal correlation functions and the state of and the black hole states. And also the black hole states are described by these Carli density of states. And you can also study the thermodynamics of the system, and not only you can match the BTZ black hole thermodynamics, but you can also compute the spectral width of the mechanical window, and you can check that it scales parametrically in C, so that fluctuations are parametrically short in time. So holographic CFD should be a very good example to apply this formalism to. And if you do so, well, you can write the correlation function in CFD terms and the completion function in CFD terms. This is just the same. If you write it down explicitly, it's the same expansion as the one that I gave you before. And also, sorry, I forgot to mention it. You can study the asymptotics of the square of the structure constants when at least one of these operators is heavy. So CPQR squared. And in a nice paper by Collier, Maloney, Maxi, and Sares, they found out is the result of large C. It's a special function C0 which is connected with the velocity formula. Also, you might want to implement ETH considering these structure constants, again, when at least one of these operators is heavy, to be random variables with mean 0 and variance matching the variance that I showed before. And this is a very fortunate choice because it's exactly the choice that, because of this paper by Chandra, Collier, Halpern, and Maloney, and also other papers in the literature like one of Alex Belan and De Boer, they match, basically these papers show that you can match Wormhole contributions in gravity from the CFD performing this choice. Then you can do it explicitly. One nice thing about CFDs is that you have different channels. You can expand the correlation function in different channels. One is the Nyquist channel, where you insert a resolution of the identity between the two operators, and you have the expansion there, which is essentially the same. It's the same expansion in the energy eigenstates that I gave you before, just in CFD terms. But you can also have a different expansion, which is the OPA expansion, where you first fuse together the two operators, and then you have the thermal circle evolution. And this is a very nice CFD property that essentially allows you to split very nicely the mean of the process and the stochastic fluctuations. And this is set by, if you take P1 prime, the operator there to be either the identity operator, so such that this is the identity block, or a heavy exchange. If you perform this choice, then okay, you basically match the gravity result, and this is the result in terms of the UV correlators that I mentioned before that can be found looking at this paper of Chandra, Collier, Hartmann, and Maroni. So the bottom line of this paper is that for the class of observables that we studied, you can set up a mesoscopic holographic duality where on the CFD side you have observables which are stochastic processes, and in the CFD you specify a probability distribution, and ADS essentially computes moments of this stochastic process. So that really you can think of ADS CFD as being a duality between a probability distribution and its moments. And at the same time, however, ADS gravity to me seems quite unique, because to my knowledge it's the only theory that is naturally defined in terms of moments rather than adding stochastic flavor to some deterministic terms. For example, in the case of Brenner motion you add a stochastic term. For the case of, in standard mathematics literature, you normally make these random coefficients this coefficient Cn to be random. Gravity, to me, is the only theory that is naturally defined in terms of moments, or at least that I know of. And the second byproduct of this study, it's maybe a bit technical, but I think it's quite nice. It's related to a theorem in the mathematics literature called the Kasami-Katuna-Love theorem, which says the following. As I said before, if you have a stochastic process, you can always expand it in a basis of function, and the coefficient in front of this expansion, Cn's, are going to be random variables. But if you do it for a generic basis of functions, these coefficients are going to be highly correlated with each other. This theorem tells you that for any stochastic process, it always exists at least a basis of functions fn, such that these coefficients Cn are uncorrelated between each other. And for the case of stochastic processes connected to semi-classical gravity, our work showed that the KKL basis is the set of conformal blocks. Now, in hindsight, on one hand, you might think, okay, we are talking about 3D gravity, so what could it be? But I think it's quite nice that mathematicians struggle quite a lot in finding this basis, and in our work, this comes out very naturally. So I think it's quite nice. Okay, and this was the comment that you asked me, so I don't have to repeat it here. Okay, so the summary is essentially similar to what we said before. We just added now that this phenomenon is really a generic feature of quantum solving systems that relies in particular on ETH, and the fact that we also found that the KKL expansions for stochastic processes are described by gravity. Let me maybe mention a couple of very quickly interesting directions. One, I think, interesting direction that could be explored in the future is to try to give a gravitational interpretation of these random fluctuations, and this is connected with can be connected with a random tensor network that people have studied in the literature, and these random fluctuations, of course, are present. But to me, this is still a boundary definition of these random fluctuations. What I would really like to find is a gravitational way to take them into account. I don't exactly know how, maybe through some string theory interpretation, or maybe what we're trying now is a path integral formulation of the stochastic process. And I don't know, perhaps we managed to find something. And the second interesting direction is to try to give a quantitative estimate to the amount of information contained in these wormholes. And here, the interesting part is that it seems that you have two competing answers. One is that if you compute higher and higher moments, it seems that you're probing finer and finer information on the theory, because you basically are understanding how the noise at different times correlates with each other, at a finite level. But at the same time, the theory is still described by a handful of parameters. So it might be too ambitious to say that we can really learn something about the UV of the theory. This is also connected with what people in mathematical literature call the Hamburger moment problem, which is the problem of finding necessary and sufficient conditions for a series of moments to be described by a positive definite measure. And so maybe we can maybe use some results in this literature to find some results for gravity. And if this fails, you might also want to study less ambitious questions. For example, try to understand if the probability distribution is unique or not. And okay, thank you very much.
Questions?
Maybe this is a little bit technical, but like when you talk about, still related to like what Pratik was asking. So you were explaining that because of there's a bunch of delta function, your axis for the like 4-point function. So like the contribution from this F4 or H4 is in general smaller than the first one, right? Because like the terms, because of the delta function just have smaller terms contributing, and later you use this to explain like the CMT calculation with with wormholes. I think it's. Could you maybe go back to the slides
to maybe these answers?
No, like sorry. Yeah, here. Yes, exactly. So the means. The mean value here, I would imagine it's like much larger than a statistic fluctuation. But like, how can I see that?
Okay. Well, yes. The reason is that I can have the light on. The reason is that one thing that I did not mention is that we always want to normalize the 3-point function, something like this, to be 1. This is the only piece of knowledge that I did not really put in here. So when E1 prime is the identity, you have that basically these two coefficients in front are for this term here are 1.
Yes.
Well, these guys here are supposed to be suppressed by factors of e to the minus.
Okay. Sorry, by factor of
e to the minus. I guess, I mean, each one of them should be e to the minus s divided by 2.
Okay.
What I think was mentioning at work was basically the variance of these guys here, and these all contribute at the same e to the minus s level. But the point is that the structure of delta functions, when you then plug it in the thermal correlation function, gives you factors of 1 over z squared.
Yeah.
And they are sublating.
Okay. Exactly.
Do those of the coefficient involve heavy operators?
Yes. So, well,
that's what I'm sure statistically.
They basically. In this result here, you only want to sum over this P1 prime and P2 prime. Either you take them the identity or the spectrum of heavy operators. Somehow, because we are dealing with pure gravity, we are setting, for example, C. Well, besides this being equal to 1, for example, C O. Let me call them light, B0. So, for example, we don't really consider situations where, if you have, for example, more than one matter operator, so for example, you have O1 and O2, stuff like C01, O1, O2, we essentially said it's zero. The reason being that you are considering an EFT where in the bulk fields are free and do not really interact with each other, they only interact gravitationally. So, for example, you don't really have interaction vertex, but they only interact through, well, gravitons, even if in gravity there are no gravitons. So this is the identity block. And expecting the operators.
Any other questions? Okay, now let's hang with the